Okay, I'll start by saying, first of all, I didn't have a chance, so I would just say that since it's in the memory of Jean-François, that I got to know Jean-François in 74, but Bad Salzufen, I see a lot of people, not a lot, but Aumann, Sergio, Elon Kolberg, Shmuel Zamir, Herr Professor Dr. Kolberg, and others in Bad Salzufen. We sat there for 2 weeks. And I have to tell you one thing, then a few years after, 2 or 3 years after, or maybe a little bit more, we've been together in Oberwolfach. And in Oberwolfach, the drinks were like open, and Jean-François used it very well. And like at 2 o'clock in the morning, he was completely drunk, but really completely drunk. He couldn't talk. So I said, I really was very curious because he was so sharp, and to see if he can function while he is extremely drunk, okay? And I asked him some question about the values of non-atomic games. At that time, he was doing it, me too. And then he was looking with the big eyes on me, and I was sure that I killed him. And the minute after, he started exactly like he was driving, fast like crazy. He would start moving me from one Banach space to another using this operator and that operator, and it landed at the right answer, okay? So I was amazed. The second thing that I want to mention, we organized in Ohio a workshop of game theory and macroeconomics. I don't know, Abraham probably remembered others. There were really a core group in macroeconomics in the audience, obviously, and some game theorists. And really, Jean-François taught them quite a bit in macro, even on institutional facts, remember? And he was the most lively person in the room, which amazed me. I mean, Jean-François in macroeconomics. And later on in Stony Brook, he volunteered to teach a PhD course in macroeconomics, okay? So the guy was, okay. The topic today is voting power and proportional representation of voters. This is a joint work with Artyom Zhelnov, a PhD student in Tel Aviv University. I don't know how it works here. This goes like this, and this goes like this. So what is proportional representation? We all know it's a system that allocates seats in parliament proportional to the number of voters. Okay? And the question, I have to, okay, now, and the question, does this system reflect the real power of parties? And the answer is in general negative. Why this is important? Not necessarily only for parties, but think of a firm, a company, and with shareholders. And you know, usually the dividend is allocated proportional to the percentage of shareholders holding. And the question, is it the right thing to do? Okay, to allocate dividends in proportion to your allocation. And in parliaments, does this system reflects real power of parties? And the answer is in general no, and that's trivial. You can put many. So let's say that we have 3 parties. I mean, you can do it even more strikingly. You have 2 m+1 parties in the parliament. M is an arbitrary integer. K is the number of seats that each party has. And let's say one party has only 1 seat, the other may have any K, as big as you want. A majority consists of at least mk plus 1 seats. Mk and any coalition with m+1 wins, and any allocation with less than m+1 has no majority. So this symmetric game, and the small coalition has the same, completely symmetric, and therefore the small coalition has the same power as any large coalition. So from that point of view, the answer is, I mean, the bargaining power of a coalition not necessarily reflect, okay, the size of that coalition. So that's the, and my question is, under what circumstances still the size reflects the bargaining power, okay? So there are some quotes from Penrose from 4652. He says, define voting power of a party as the probability of that party being able to influence a decision either way, okay, in favor or not. And then he conjectured that asymptotically, the ratio of voting power to size is the same across parties. So let me just, before doing that, I want to say parties, which is a little bit different, but for those that I would say, I don't know how to, sorry, I will see you in a second. So suppose that, let me first talk about when the players are infinitesimally small, okay, that everyone has negligible effect. In that case, if I'm talking about a game of a weighted majority game, this will look like this. So you have a function f from, let's say, 0, 1. Let's say that the set of voters are lying in 0, 1, 2, 0, 1, so that f of 0 is 0 and f of 1 is 1, and I can measure every player, the measure of every player is 0, but measures of coalitions are, let's say, by some measure mu, can be Lebesgue or others. So the gain V of S, what coalition S can get, is f of mu of S, but it is defined. Let me first, let me say what is f precisely. So f is a jump function. F of x is 0 if x is smaller than q, some quarter, and 1, maybe smaller or equal, and 1 if it has a higher quarter. Okay? And then the game is V of S is f of mu of S, which is if the coalition S has a majority, namely over the quota, it gets the full power, otherwise it gets 0. So this is well-known class of games in the literature, and Aumann and Shapley extended the Shapley value axioms to deal with non-atomic games. And this kind of game lies in a well-known space. They call it BV prime NA, but doesn't matter now. And they proved that axiomatically there is a unique value on that space, and actually the value is the value phi of Aumann-Shapley of V of S is simply the mu of S. So your value is your measure. From that point of view, the proportion, so this is the bargaining power, if you like, to interpret the Shapley value, the Aumann-Shapley value of a coalition. And the value of a coalition divided by the size of the coalition is precisely 1. Okay, so if I want to see what is the ratio of the bargaining power to the size is mu of S. That's the value. So this over mu of S is 1. Now, Neyman, in a famous paper by him coming from his dissertation, proved that not only this value is coming from the asymptotic, from the axiomatic value, but also it is an asymptotic value. In what sense? If you start cutting the set of players into small pieces, and the pieces may be of different size, even the ratio between pieces may be infinity, but they are all very, very small, then and each time you look on the V, the game restricted on those coalitions, it becomes a finite game. You look on the Shapley value of that game, it has a limit in the very strong sense, and the limit is again mu of S. So this has asymptotic, very crucial asymptotic result, and also axiomatic. So it is justified axiomatically and asymptotically. This is, however, for that you have to assume that every player is negligible and only coalition has a sizable effect. Okay, is this clear? Now when you are talking about parties, you don't expect parties to have negligible effect. Some parties should actually, but this is not always the case. And therefore the question, as I gave you the example here, it's usually you get negative. I mean, it doesn't reflect, bargaining power doesn't reflect size or size does not reflect bargaining.
So, wait a minute, let me get this straight. Can you bring back the previous one? Okay. You're intimating that Penrose's conjecture is verified by Neyman's theorem, or by...
No, because, I mean, in a sense, okay? No. I mean, he probably was thinking, there was no Banzaf at the time, but he was the, yeah.
Being able to influence the Shapley value, taking that as an assumption, that's the definition, then the conjecture is verified in the sense of Neyman or Amon Shapley.
Yes, not really necessarily. I think that what he meant in the ratio, because what Abraham did, or you, is, well, in a sense, yes, you're right. However, for that, you have to assume that all parties are infinitely small. Yes, exactly. Yeah. So I want to see how it is when you want to refer to not necessarily small parties, what can we say then? Because the example before shows that you get that this is not the case in general. Okay. So what we use here, yeah, okay. What you use here, okay, is what we use is the Shapley value, or Shapley Shubik for voting games is the Shapley value for voting games. And we'll talk about a little bit about the Banzaf, okay, about the Banzaf later on. Okay, so the main result, if party size add up to 1, okay, and is uniformly distributed, I'll say a word in a second, the expected ratio of a party size to its political power I measured as the Shapley value, okay, converges to 1, and actually it increases to 1, and the rate of convergence is high, because what you cannot get, for instance, from the methods of Abraham, is the convergence rate. And that's very important. If parties do not have very, very small size, then you may, the convergence rate, I mean, is very crucial to see how fast it is going to 1. Okay. Now I'll say about uniformity in a second, okay? So first of all, the model, and then so let n, okay, be the n up 1 to n be the set of parties. x1 up to xn are n random variables on the simplex. Namely, they add up to 1. Each one is non-negative. And let's say an is the simplex, which is all possible realization of the n tuple of random variables. It is assumed that the realization has a uniform distribution on an. Now, you may object right here to say, because sometimes you see bigger coalitions, bigger parties, and it's not, or in many parliaments, you may see bigger parties, and therefore, why should we assume a uniform distribution? First, we assume because we know how to answer it. But I can tell you, for instance, if you take 10 parties, when party size are uniformly distributed on the simplex, the probability that at least one party is larger than 20% is very, very large, 92%, okay? And the probability that at least one party is larger than 30% is 40%, is 0.4. Now, I didn't write it here, but the probability that at least two parties will be bigger than 20% is about 40%. So it's not, you can't say by looking on that you get something that you don't observe necessarily. When n is large, more than 10, I didn't check. I tell you why, because... Of course. It's going to be, of course, it's going to be very, very close to the center, okay?
The maximum size, when n tends to infinity, the maximum size
is small.
To 0.
Yes. Okay. Yes. Now, what is the game? So here is the definition of the game. I take any quota larger than, I take any quota in between half and 1, not 1. And let's X the weights, system of weights, B realization of party size. Vn, the voting game, is defined as follows. Very simple. If you have your bigger than the quota is 1, and otherwise 0. We refer to S as a coalition of parties. So we have parties. We're talking about coalitions of parties. This clear? Huh?
XI is the size of party.
Yes, Xi is the size of the party I. Okay? And the sum of the Xi's is 1. Okay. A winning coalition, actually I don't use it, but so let's say a party is pivot to a coalition S if S has no majority, but with I it has a majority. So this is a pivot, and for any X system of weights and a player I, theta IX denotes the set of all coalition that I is a pivot there. Okay, so theta IX is the set of all coalitions S so that I is a pivot to S. What I mean by pivot, it changes a losing coalition into a winning coalition. Okay, without it, no majority. With it, you have a majority. The Shapley value is simply the probability to be a pivot. Now, what are the probabilities of coalitions? So the equivalent of the Shapley value of a party I is the probability that I is a pivot to a random coalition, where coalitions of the same size are equally likely to be formed and all sizes have the same probability. So Shapley, that is a result of Shapley by imposing 4 well-known axioms. I'll write down in a second. So there is another axioms by, but I don't think I use it and I'm not sure I have time. So Young characterize it by not using the additivity, but I'll go on that. And the theorem of Young is the Shapley value is unique, but that's Shapley 53, Young 85 is a different version of the Shapley value. Okay. Now I'm looking on the expectation. So given X, okay, a realization, if you like, of X, this is a random variable. I look for every I look on the Shapley value of party I, dividing by its size, given the number of the number of parties, which is n, and I look on that. This is simply the expectation. It should be small x dx, and where rho n is simply the inverse of it. It's the volume of an. So this is simply we're talking about the expected value of the ratio between the Shapley value and the size. Theorem. Where is number 3? So I didn't look on. Okay, so I don't have the. Huh? That doesn't matter. I would say in words, or I'll write down in the. Because number 3 was a result by Neyman, so I thought that I sent it, but maybe this is not the most updated. But oops, sorry. What is the theorem? For every I and for every quota, if you look on the expectation of the ratio between the Shapley value and its size, it is increasing in n and converges to 1. The second one is that the convergence rate is of the magnitude of 1 over n.
How far away is the ratio of 1? The expectation may be close to 1, but
It may be.
Always far away from 1.
It may be, the example that I gave, it is like this, okay? If you have one small and all the others have big ones. So I'm talking about the expectation. Now the expectation, a priori, you want a voting mechanism so that it will work out even for any parliament. You don't do the rule. Huh? Yeah, the Neyman's result. Neyman results talk about.
Get small parties. It's okay. And then tends to infinity, the parties will be smaller from the 1.
The Neyman results will say that actually in expectation, the sum of the expectation of phi of
You know, we're not talking about the error term, okay? The error term is very good, but without the error term, that it tends to 1, okay? That it tends to 1, without the large O 1 over n. This follows from name and sheet.
Yeah. No, I mean, it tends to 1 in what sense? In the expectation?
Probability 1.
Probability is not enough because this is not bounded. This is not bounded.
Oh, you're right. Okay. Probably with an expectation, you say it doesn't.
In expectation, no problem. What Abraham proved is the expectation of the sum of I to n of phi I of x minus xi. This goes to 0 as n goes to infinity. This is the result of Abraham. Am I quoting you correct? Bob?
No, I don't think so. I think the result of Abraham is that Bix over xi minus 1 goes.
But you ever hear a dispute with the author, so I...
It's a distance between the two measures. It's right. It's a distance between the two measures. One is the value, the other is the mu. That's a distance between the two measures.
This is the result of Neyman, which means that the expected, I mean, in expectation, the difference goes to 0, not the ratio. Okay? The conjecture was about the ratio. But in any event, that one doesn't give you any clue. Just one second, Zvika. It doesn't give any clue to the rate of convergence. And the rate of convergence, as I will say, just 1 second. Why don't you ask? Huh? A big N is the set. N is 1 up to N. Is the set of parties. N is the number of parties. Small n is the number of parties. Capital N is the set of parties.
Look, you could have written there sharply sub 1 divided by x1. Doesn't matter.
It should be 1. It should be 1 here. Okay? I tell you. It should be 1. Or if you want, if n for fix I and take n large. But let's say 1. Okay, put here 1. I mean, I don't have the updated slides here. I thought that I sent. And the use symmetry. So you should write here sharply value. One when n goes to infinity. Okay, this is the. Phi I, yes, this is the Shapley value of player I. Okay.
Yeah, would you write sometimes SH? SH equals B.
Okay, SHI of x minus xi. Who wanted to ask? Yes. Always less than 1? Because it's no. I have no. I don't know. Actually, it's a good point.
It's concave or something. So it's less than the one of then the ratio of the expectation.
I can tell you. I mean, maybe, but look, it looks like this. So the expected ratio of the Shapley value to a party to its size for a simple majority game, quota is half, by simulation, looks like this. So it's increasing and goes to, so it's concave. Yeah. But
The question of Joe is very good.
yeah,
It would be interesting even to know why
it's increasing.
it's always below 1.
Why it is below 1?
The value
I have no idea.
is very good.
Yeah, I should think of it. I don't know. Okay. Yeah. Okay. Pardon me? Yeah, of course. But I mean, you probably can characterize, which we didn't do. I think for Abraham result, it's enough that that the mass, I think, goes to the center. I mean, to 0. But I don't know to characterize all. I mean, all the distributions that give you that result. I don't know. But we should do it, but I don't know. Okay, about the proof is going very close to, so the proof uses, I'm not going, but just to say, you fix, for instance, the size of party 1 to be C. And then you look on C and C to be the simpler X, but when you fix 1 with C, and then the others anything, okay? And then you use two points here. One is that if you have y1 up to yn, it's probably well known in statistics or whatever, if you have y1 up to yn, which are exponential distribution, IID, then the simplex, okay, has the same distribution as y1 over the sum, etc., etc. And the other one is to see that the summation of the xi has beta distribution. You use that with that parameters. You use that to prove that what is first the Shapley value on average, the average Shapley value, given that a player has a weight, the player 1 has a weight c, and this, when, if you like, when n goes to infinity, it's c over 1 minus c, which is the result of the Oceanic game with one large player, monopoly, how do we call it? Oligopoly, whatever, okay? Atom. And then, I mean, you can figure out that this is the right thing, and then how you proceed from that, you just, again, it's not in my slide, so I will not mention. Then you condition on that one, and you do and you get something like this, and this is the, for Q equals 1/2, you get that formula, and maybe you can check that this is a concave, probably. Okay, I didn't do it. Okay, but in any event, that is this goes to 0, and this is over something that goes very fast to, I mean, 1 minus the size of 1 over n. Okay, of the magnitude of 1 over n. So you get something like this. Next, okay, so what about the variance? The variance of the ratio is very fast, goes to 0. Okay? So the variance of the ratio of the Shapley value to a size looks like this, and it converges to 0 very fast. Simulation. Many things, I mean, the result I tell you now is analytically. I'll tell you exactly when it's a simulation, when it's not. Now, if you want to, okay, that's what Abraham Neyman proved. So the probability, from Abraham Neyman, and you can prove that actually the ratio, the probability is very small, goes to 0, of the difference between that and 1. That you can prove. Okay? But that does not imply anything about the expectation, since it's not bounded. So, yes. It follows from part of his thesis.
I don't remember that he talked about the uniform distribution.
No.
But it follows from it.
Yes. Probably you can say a word about what are all the distributions that give you that result? Anything that concentrate around the center?
Definitely for the distribution, the sum of all the xi where this doesn't happen is small. You, instead of probability, you would look on the set of all I such that this is not true, this would be very small.
Okay, fine. Okay, sorry. Now, by the way, in the Netherlands, we did the following exercise. What we did was the following. Consider the election of the second chamber, Tweedkamer, of the Netherlands Parliament. We analyzed all elections since 1918.
This is the House of Commons.
Yeah, in the Netherlands.
That's the important house.
Yes, I think so. And why 1918? That was the first time the PR system was introduced in the Netherlands. For each party, we compute the ratio of its Shapley value to its size, okay? But we then took average over the parties because parties change from election to election, so you couldn't follow one party all the way. So when we look on it, for each election, we compute the average value and the variance of this ratio. And it looks, if you look, you see that quite close to 1. It's look quite good. So that's the average ratio. This was the variance, which is close to 0. At some point here, since it becomes small, the variance is a little bit bigger. And this is the number of parties. So I think that we want to look on this one. Okay, so it really, I mean...
so this split is when the parties were
very small. Yes. So that's the variance become big. And it doesn't converge. So it looks as if it is in our way, okay? It's in the Netherlands. Okay. Now, suppose that you allow all parties are larger than t. You fix n now. Fix n. We fix n the number of parties. We take t smaller than 1 over n. Namely, we only consider the simplex, but elements in the simplex that each weight is bigger than t for every I. Then the case of n equals 3, you can analyze it analytically. And what it says is that the expected is exactly 1. Does not need to go because n is fixed. The expectation is exactly 1. So there, I should say, there exists t where you get it exactly. So maybe you want to use it as a suggestion for what should be the threshold, if you believe on that ratio is important. Okay. If you want to... You did the simulation. You remember what he was? By the way, this is Artyom Zhelnov, my co-author. Yes. Yes? What was it exactly? 20%. Okay. I have 5 minutes, so give me a chance to finish. Okay. If you want to eat. Now, this proposition is for any n. This proposition is only by simulation, so it's not analytically. It says suppose that n is odd and q is half. Odd. Then you get that the expectation is and x is uniform distribution on t, and you take there exists a t where it's exactly 1. Otherwise, if it's even and the quota is half, and x is uniform distributed on t, tn is the elements in the simplex that each one of them is at least t, okay? Then it's close to 1 as t goes to 1 over n, and it's fixed. Now you move the t. Okay. What about the Banzhaf? The Banzhaf is exactly also the probability of being pivot, but I give to every coalition the same probability. So the probability of all coalitions are the same. So if I am player 1, number of coalitions that do not include me is 2 to the power n minus 1, and each coalition, okay, gets the probability of 1 over 2 to the power n minus 1, and therefore the Banzhaf is the probability of being pivot under this distribution. So I again can look on the ratio for the Banzhaf, and that gives us completely something, it goes to infinity. What about, and I don't have it here, what about the normalized Banzhaf? So the normalized Banzhaf was proven by, also I think numerically, by Machover, used to be in the Hebrew University. And Machover proved that just for Q equals half, not proved, but by simulation showed that for the Banzhaf it tends to 1. But if you change the quota, different than half, the Banzhaf does not converge to, either does not converge or does not converge to 1. I'm talking about the normalized Banzhaf, where I take the Banzhaf, I sum the components, and I divide it by the sum so that the total will be 1. So it doesn't converge. But that's, now, if you divide it by square root, there is some good explanation why you may want to consider that. Then you get the Banzhaf, the expected ratio is very, very close to half. That it's not very important, but it converges to a point. Okay. Finally, I wanted to say, I have 3 minutes, so I'll go very fast here, and then I'll finish. What happens if you have ideological space? Okay, so then there is a, okay, so to deal with ideological proximity of parties and voters, it is assumed that parties and voters are located in ideological space D, which is a subset of RD. So you may have not only one dimension that varies from party to party, but they can differentiate themselves in many directions, okay? Where D is the number of factors for voters' position. Every point in D represents a voter. The Euclidean distance between any 2 points in D represents an ideological difference of voters and parties. The assumption is that every voter votes for a party that has the smallest proximity to his or her location. Okay? So how it goes? First, I want to say, yes, parties choose their location, Y1 up to Yn, and I don't know strategic here. In D, independently, they choose it, and according to some density distribution F. It can be the density, maybe from some strategic considerations. Voters are located in D also according to the same density distribution F. So you have parties location in D, okay? We'll see a picture in a second. This is D, and you have the voters, and you have some parties located in the same region. And now, what is Li? Li is the size of party I, namely, the set of all voters that are as close to that are closer to I more than to any other one, to any other party. So Li is the set of voters that will vote for I, okay? Set of voters that closer to party I and to any other party. The size of party I is simply the integral over Li. Now, what is the Shapley-Owen index? It measures the voting power of each party, taking into account their locations, as follows. And now I'll tell you just by a picture. You take the unit ball. Maybe I go fast, but just to give you the intuition. Sergio, don't do the concavity now. Look on here. You take the unit ball, okay, and with D dimension, with the same dimension as capital D, and then every omega, namely every direction, okay, so here's the unit ball. You take a direction W, omega, okay, and then you take the projection of each one of the parties on the line that goes from 0 to omega, okay, in this direction. And then this is the first one, this is the second one, and this is the third one when I look on orders. So I order the parties according to their location in with the omega. So for every n tuple Y1 up to Yn, Y in D, together with an ideological direction, it defines an order of parties, R, W, Y. This order is generated by the projection of Y on the line connecting W to the origin. Okay? So that defines all kind of permutations of the parties. And then what we do, for every I, we look on that, be the set of parties in N that precedes I in the order R, and the Shapley value, or the Shapley-Owen index, is the probability of I to be pivot in a random order R, W, Y. That is, you take you look on the difference between what the marginal contribution of I to that order, that all of the parties that precedes I in that order, and then you multiply by the density, and then you take you take the integral with respect to that.
It's not random order, that's random direction.
Random direction, yeah. And that's the Shapley value. Now, we don't...
You have a random order induced by the random direction. Random doesn't say uniform. Random says random.
The order induced by the random direction.
Exactly, by the random direction. So you integrate it by the directions also. Okay? Now, we have nothing to say analytically about it. Okay? Sorry. However, if you look, taking the distribution of Y1 up to Yn into account, we can compute the expected ratio of the Shapley-Owen index of a party to its size. We consider the one-dimensional ideological space for the simple majority game when locations of parties and voters have uniform distribution. You get that the ratio is something like this, but it is not far away from 1. Okay? And if you take D equals 2, and that's my last slide, and you do Monte Carlo simulation, and you take D equals 2, and the simple majority, you take simple majority gain when locations of parties and voters have multinormal distribution, you get something like this. Yes, yes. The same ratio, and you get... so we provide some justification, okay, for the proportional representation rule, by looking on the expected ratio between the two, and somehow we confirm the conjecture of Penrose.
We also implied that we should make the lower bound of representation 0, because you need lots of parties for that.
No, I mean, as I said, look, Sergio, even with 10 parties, let me go, I consider it as a question after the talk. Look, here, even with 10 parties, you are very close to 90%. And you know how many parties? I don't remember, but you check, let's say in Germany, before election, it's really if you have or don't have threshold, but sometimes you have 30 parties competing. Okay, it's not that small size. The uniform may be, but I told you, I gave you, okay.
Well, okay, here's another question. Okay?
Yes.
Question period. Comment really. Over here, we now have a bill in Parliament to.
Hello, Cole.
We have a bill in Parliament to raise the what's it called, the threshold of representation. Yeah, this is an argument to lower the threshold. Yeah, so you have more, as many parties as possible. You know, in fact, you could increase the size of Parliament also. So you could have a lot of parties, and this will make for a better democracy, a more democratic thing.
In a sense.
No, he didn't tell us what is the effect of the threshold T on the convergence. We don't know that.
No, if you have a large threshold.
Result on that?
No. I mean, the threshold at the beginning we say the T with the T for any N. Okay. Yes, אחוז חסימה. Of course, that's the point. It changes.
The higher the threshold, the fewer parties you're going to have, right?
Yes, correct. But if you still believe that
if you
don't change
the threshold, you can have more parties, and
more parties, and therefore you are closer to one. On that remark, I agree. Okay. In the break, we can talk.
Just last question. Yes.
I don't say it. I'm not saying, by the way, I don't claim it. I say we see in reality that proportional representation is, in what sense you can justify it. That is one way to justify it. I'm not pushing that it should be, why, you want to say why bargaining power should be somehow reflects the size, or the size should reflect the bargaining power. That is your question? I say, I take it as if this is the desirable property, okay? Why is just to give justification to what we see, okay? No more than that. For instance, in Israel, in the Netherlands, in Germany, you see voting, that is proportional representation. Parties get seats in the parliament proportional to their size, to the number of voters. Now, my question is, pardon me? What do you mean by definition? But no, that's for sure. That's the definition. So that's the definition of proportional representation. That's the definition. Now my question. That's exactly. So we use the Shapley value. That's my... Huh? In the Netherlands. Look on the Netherlands. You see the Shapley value over the size, give you exactly 1. It's very simple.
Okay, I think we should stop now.
Good.
There is lunch, that you So yesterday,